Okay, that one went to YouTube, so I seem to be on a roll. I'm going to keep going. Here we go. Kinetics of radioactive decay. I'm more concerned with us being able to do the reactions and then being able to do the half-lives. So I want you to, this is what I care that you can do right here. The main types of radioactive decay, alpha particles. I want you to know what alpha particles are, beta particles. These are gamma rays, which we are definitely going to talk about. Very short wavelength, but the most penetrating and the most powerful. I also want you to know what electromagnetic waves are, and electron capture. We're definitely going to talk about these, but I mostly want you to know what the particles are, not so much the calculations. All right, so that's what we're going to talk about. So I do want you to know what radioactive decay is. Please keep in mind that it is all based on stability. I've said that several times. Remember, in nature, everything wants to be balanced and stable. And so if you have an isotope that's not stable, where the nucleus is not stable or becomes unstable because maybe I don't know, you shot something at it like an accelerated particle. They have one of those in Houston, a particle accelerator, and they fire things. You know, that's how we get a lot of our nuclear reactors and our nuclear weapons now. So we purposefully shake up a nucleus and make it unstable so that it will decay. And we use them for a lot of important things, so it's not necessarily a bad thing. But radioactive decay is where things get shot out of the nucleus so that it will become more stable. And this is in your textbook, where in this particular one it's uranium-238, which is what was used in the bomb. And so it gives you a series of the reactions that it's going to, and this again is in your textbook, showing that it goes from uranium, it alpha decays, to thorium, and then it beta decays, and then it beta decays again, and then it alpha decays, and it keeps going to a series of reactions until finally, it gets to lead. And lead is very stable. And so it stops, and it stays there, because the mix in the nucleus of protons to neutrons is just right. All right, so that balancing of nuclear equations is very important. We talked about that. Remember how we talked about that, and I gave you some to do, and I'm probably going to give you some more. This right here, being able to do this, that's 238 on the top there, so this top up here must equal 238 as well. This subscript down here is 92, so these two together must add to be 92 also. And the same step is also true. Each reaction has to be balanced along the way. It must stay balanced. And so that's what it's talking about there, and that's what you'll be required to do as well. Okay, and so the original element is called the parent, and each after is called the daughter. It's called the daughter in this series, the product. Okay, and so then you're going to just well, I won't ask you to do that, so you'll be good to go. And so here's these here are talking about half-lives on the right-hand side over here. This is talking about how long the half-life is. 4.51 times 10 to the 9th years. That's the half-life. And let's talk about what a half-life is. You can find half-life according to this. And this, see, I would personally do this a little bit better. The ln of 2 is equal to the negative k times t. This is just a simple logarithmic from college algebra. The ln of 2, which this is taking the at time 0 and at time t. So actually that's at 1/2. I shouldn't have said 2. It's at 1/2. So if you want the half-life, you're finding out it's a period of time, the time that it takes it for half the original amount to decay. That's what you're looking for. So that tells you how much is left. And you can rearrange and get that. So this right here is the ln of 2. That's what this is right here. So the original amount that's left over, if you want to find the half-life, that's what you're going to get right there. So for uranium-238, notice what the half-life is. It's a huge long time. And yet for polonium, it is 1.6 times 10 to the minus 4 seconds. It is so short, as a matter of fact, that they can't even, if you look on the periodic table for number 84 polonium, it doesn't even have an atomic mass. It's in parentheses like this, because its half-life is so short they can't even keep enough of it on there long enough to get an accurate measurement of its mass. So they only had to guesstimate what its mass is, its atomic mass. But that's what half-life is, and I care more that you know that half-life is the amount of time that it takes for half of the original sample to decay. In other words, if you have a sample and you have 100 grams of that sample, after one half-life, now you only have 50 grams. After another half-life, now you only have 25 grams. After the next half-life, now you have 12.5 grams. And after the next half-life, and it keeps going on and on and on. And you'll never get down to 0. It's just going to keep cutting it in half, cutting it in half, and cutting it in half. So this then would be 6.25 grams and on forever. That is what half-life is. But we can use half-life for some very, very important things. We have used them in carbon dating. We also use them as radioactive tracers in medicine. Okay, here's the equation that is used for carbon dating. We use, this bottom one is what's used in carbon-14 dating. That's what's used there. But I also want you to know that what we use carbon for, and it can tell you the carbon-14 dating. The problem with carbon-14 dating is that after about 4,000 years or 4,500 years, carbon dating can be very unpredictable. But it can show you how to calculate how much you would have left after a certain half period of time. I'm not going to ask you to do these. I'll care more that you'll know about these transmutations right here. These are the ones that I care more that you can do. Nuclear transmutations right here in section 20.4. I care that you are able to balance those. I care that you know that if you can convert or mutate one element into another by bombarding it, okay? Okay, I'm sorry I got interrupted. Again, this is alpha being an alpha particle being shot into a nitrogen atom. That's what's happening in this case. So this would be called bombardment or absorption. That's what's happening in here. But again, you're going to add these two top numbers, and so on the left side or the reactant side, there's 18 total. as the superscript. Well, that looks terrible. There's 18 total up top. And in the denominator down here, there's a total of 9. So our superscripts up top over here, that has to be our target. Okay, they have to add to be 18 up top, and they have to add to be 9 in the bottom. So as you can see that they've done that. So that's going to give us an oxygen isotope, and then it's going to shoot out a proton. All right, and so it's talking about here in the text that this reaction is talking about, is it feasible to convert one element into another by nuclear transmutation, and if it makes sense to do so. And this is talking about collision reactors and things like that. So it's different from radioactive decay because radioactive decay happens spontaneously. Transmutation happens because we're colliding, we're forcing it, we're shooting things into the nucleus. All right. So transmutation is noted with special symbols, but you're still going to do it in exactly the same way. Same sort of reactions, same sort of balancing the left and the right side of your yield sign. But I do want you to notice this abbreviation right here. Here's your alpha particle. So you have your little set of parentheses. Here's your alpha particle, a comma, and here's your proton. And that could also be an H for a hydrogen, for a 1,1 hydrogen. So the comma separates the reactants and products. So this is saying that you're shooting in an alpha particle and it is giving off a proton, which is exactly what this says in this reaction. You pushed in or shot in an alpha particle, you bombarded it with an alpha particle, and it gave off this proton. Alright, that's good enough. And so here's an example for you that's in your text sample problem 20.5 that's in your textbook. Let's do this without cheating, without looking at the answer. It's asking us to write the balanced nuclear equation for the reaction that's represented by iron 2656. So if we have, and it's being bombarded by D, and it tells you where D is a deuterium. Deuterium is a hydrogen nucleus. The deuterium, this deuterium stands for 2. So that's what that's talking about. So you have a 5626 Fe, and we are going to bombard it with deuterium. So that's a 2,1 hydrogen. And so it's going to emit an alpha particle. You need to remember what's the symbol for an alpha particle. That's a 4, 2, and you can use an alpha particle like so. And then manganese 54, 25. And it's okay whether it doesn't matter if you put the alpha particle first or the manganese first. You could have swapped places with those two and would have been just fine. Alright, we're good? Those are the kind of things you're going to be expecting. Make sure that they add up to give you what is supposed to. Alright, on this next slide, don't forget that Z just is the representation for an atomic number. So then particle accelerators, we talked about those two. Particle accelerators made it possible to start synthesizing elements, and that's exactly why some of the elements that are on your periodic table are kind of transparent, because those have been synthesized using particle accelerators in a lot of situations, a lot of instances where they used particle accelerator to bombard a nucleus and make them absorb particles, and that's exactly what's happened. So this next page, which I'm not even going to sit on for very long, you can see it in your textbook, is the ones that have been so done. And at first, because a lot of this was done at California, Berkeley, the University of California, Berkeley, they started naming them after famous people and after planets: Neptunium, Plutonium, Americanium, Curium, and then they started naming them after famous people like Madame Curie and people like that. And then they started naming them after Berkeley, Berkelium, Californium, and then Einsteinium. And so then they started naming them, eventually using the Latin for the word, for 114, 115, and so forth. Those last ones that have the like 115, 117, 118, uno octimum, octium, that's the Latin. That just means 118. So, and then this is exactly what this is talking about right here. Light elements can be also made to be radioactive by bombarding theirs. So this is more of these kind of reactions, and you might be asked to balance them. So if you bombard them with a neutron, you can get tritium and an alpha particle, and so forth. Okay. All right, and then this is talking about, here's a particle accelerator right here. And then this slide is talking about nuclear fission. And this is, please do not misunderstand the difference between fission and fusion. Fission, you're taking very heavy elements like uranium, like plutonium, like Einsteinium, some of these heavy, heavy elements, and you are splitting them apart into smaller elements. And you can do them by bombarding that, and this is how the bombs were made at first. And they shot a nucleus with a neutron and split it apart into smaller, more stable nuclei. But please notice this is what I want to show you right here. See this 3 right here? That means it gave off 3 neutrons. And each of those 3 neutrons would in turn, they got shot out with light speed, literally. And they could go and then slam into another nucleus. And this set off what was called the chain reaction. And that chain reaction is what set off that nuclear bomb that they dropped on Hiroshima, however you want to say it, and Nagasaki, that ended World War II. Okay, so you can easily balance this equation as well. Just make sure that the numerators all balance the denominators. And then it talks about how much energy can be given off. And so for this particular reaction, for 1 mole of uranium-235, look how much energy. 2 times 10 to the 13 joules, which is so much energy for just 1 mole. And then if you multiply that times the mass of uranium that they used on the bomb, that is a huge amount of energy. So what they had to do to keep the bomb from going off early is they split it into 2 chunks, each of which was not enough subcritical. You had to have what's called a critical mass, enough to start that chain reaction working, so that it, like a string of dominoes, that if you hit one, it hits the others and the others and the others, and fires off very, very quickly in a chain reaction. So they had to split those into 2 pieces, and then when the time was right, slam them together like this. So when the amount of fissionable material is big enough, greater than what's called the fissional critical mass, then a chain reaction can be set off, and those leftover neutrons can get shot out literally at light speed. They can hit another nucleus, which can split it, and it keeps the reaction going, and it can generate a huge amount of energy. This is what they did in one of the very first atomic bombs. And then they used plain old ordinary TNT on each of the 2 halves to force the 2 together to make a subcritical, that each of those 2 halves be a critical mass. They slammed them together with you see what I'm talking about right here. This was, imagine a baseball, because that's about how much uranium that they used. Here's a, let me get a different color, you can't hardly see that. Here's a piece of uranium right here. Here's a piece of the uranium right here. And you see that this piece right here fits nicely into right here. And neither one is big enough. So what they did is they took some TNT and they literally blew up this TNT so that it would force this to fit like a glove into that. So that when they join together, they make a critical mass of uranium. And then right inside this little chamber right here, they had your little particle accelerator that had the first particle to start things off. And they fired that first neutron into the uranium, and boom, 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 there it went. That's exactly what happened. And they waited until that bomb was far away from the plane before they detonated that first one, and they pushed the little plunger in on that bomb. Okay? And then they also use it to generate, and still do, fission. Okay? So we use rods to control the reaction, and here's some goods and bads about those modifiers. Water is what's used to slow it down as a moderator to cool things and slow it, and so that because hydrogen is so light, what they use is deuterium instead, heavy water. Instead of using 1,1 hydrogen, they use 2,1 hydrogen deuterium in that heavy water. So this is kind of what a nuclear fission reaction looks like, or reactor rather, that generates, and it's totally cool. And they use these control rods when that reaction gets too fast, too overheated. They lower these rods to keep the reaction from happening in between them, and then they use water to slow things down and keep things cool. And then the last thing that I wanted to talk about on this particular slide is this right here. We haven't talked about this symbol. This is a gamma ray. When you do take an element, in this case cadmium, and you bombard it with a particle like a neutron, and it shakes things up in the nucleus, maybe that nucleus doesn't shoot anything out of it. Maybe it just keeps that neutron, but it shakes things up in there. That's still going to generate some energy. It's still going to release some energy. And if that happens, that nuclear energy that gets released is called a gamma ray. And a gamma ray is pure energy, the most penetrating, fast-moving, highest frequency energy that there is, that we know of as of right now. And that you don't have to balance that simply because that is, it's pure energy. There's no matter involved in that. So you would not balance that. But if it tells you that it is gamma radiation or releases energy there, then you would have to show that with a gamma ray. Okay. And this is what I was talking about on this slide about deuterium, heavy water, and they're using on this one. I accidentally went to the wrong slide. They're using D2O. This D2O is heavy water, hydrogen, this hydrogen instead of this hydrogen. Okay, 2,1 hydrogen. So that it's heavier than normal water, and so it can really slow things down. And it's hard to make, so it's quite expensive. but it works well. All right. And then here again is your reactions that take place, and I'm going to let you work on balancing those. I've shown you several of those and how to balance them. I think you got the idea. Okay. And then this is just talking about breeder reactors, which is where you're taking uranium and you're mutating it into plutonium. Now, what do you do with it? What do you do with the rest? You know, right here it tells you it takes about from 7 to 10 years and to regenerate enough material to refuel that original reactor. And that's called the doubling time. So you're going to try to reuse these, all right, and conserve so that we're not generating a bunch of nuclear waste here, but some is. And so here are some of your disadvantages. They're very expensive, very expensive. They're also very technical. You have to have precise equipment, very technical involved. There is a risk of accidents. Chernobyl is, in my mind, because I remember where I was sitting. As a matter of fact, I was sitting in a chemistry classroom when I heard about the Chernobyl explosion. I was in college, and I remember to this day sitting and coming in. There were two of those kind of disasters that occurred when I was in college. One of them was the space shuttle exploding on takeoff, and the other was the Chernobyl accident. And then how do you get rid of the waste? All right, so that's all I'm going to talk about.